Winegard Walk is the main north-south pathway through the University of Guelph campus, starting at the bus loop and going all the way to the north residences. Along this route exists a large ramp between the McLaughlin Library and the MacKinnon building. This ramp is 32 meters long with a grade of 8.75%, and like the rest of Winegard Walk, requires a winter maintenance strategy to ensure it is safe to travel. It is currently plowed and hand shoveled to clear snow, and then salt is applied to fight ice buildup. This situation has multiple flaws. First, the ramp dimensions do not meet provincial accessibility building codes, which state that a ramp cannot exceed a grade of 6.7%. In order to meet these standards, the university has concocted a to-code route that requires an elevator and looping turns through the MacKinnon building to get from the cannon to the library entrance. It would be much easier if everyone could just walk up Winegard directly. Next, when the road salt dissolves into chloride and sodium ions, it harms campus infrastructure. The chloride ions are absorbed by the porous concrete and corrode the internal rebar and steel reinforcement. The magnitude of this impact was demonstrated last summer. The university spent $100,000 to repair structural damage at the north entrance to the UC as a result of chloride ion corrosion. This was only a tentative repair, which will be resumed in the summer of 2020, adding further to that cost figure. Finally, any ions not absorbed by the concrete are washed away in the stormwater, where the environmental harm begins. These ions mobilize cations, which destabilize the soil, and in waterways they increase the pH and contribute to ammonia toxicity of aquatic organisms. Additionally, the high foot traffic of the ramp means that salt is difficult to apply effectively. Thus, an excessive amount of salt is used, compounding the corrosion and environmental issues. Clearly, the current ramp requires an accessible configuration and a winter maintenance strategy that eliminates the associated negative consequences.
Increasing the accessibility of the pathway will require two things. Firstly, it needs to be reconstructed according to updated building codes and regulations, and secondly, it needs to be maintenance-free during the winter. So this first requirement is relatively simple to implement as the answer is already written within provincial accessibility regulations. However, instead of looking specifically at ramp standards and slopes, we looked at what constitutes a pathway. So according to section 80.23 of the Integrated Accessibility Standards, the maximum running slope of an exterior path is 1 to 20, or 5%, and so we measured the elevation of the ramp to be 2.8 meters, and in order to achieve this amount of rise given the maximum grade, our pathway would require a run of 56 meters. So luckily the footprint from the corner to corner of McLaughlin is 58 meters, so this just fits within that footprint. So this design will also fit seamlessly with the newly proposed library entrance on the north side of the building. However, adapting the MacKinnon entrance and the old library entrance is not within the scope of this ramp design. The second design objective involved preventing snow and ice from accumulating without salt or people power. And we've considered traditional ways of using electrical energy or boiler heat to melt snow, but concluded that they were energy intensive and therefore costly to operate. For example, it would cost upwards of $230 a day to run an electric heater, based on current utility charges and Guelph's climate normals. So further brainstorming revealed an alternative that was cost-effective to operate and required virtually no maintenance.
After considering multiple design possibilities, it became clear that a hydronic heat system would be a suitable alternative to prevent the accumulation of winter precipitation on Winegard Ramp. A hydronic heat system facilitates the heat transfer between a working fluid and an area that is to be heated. Simply put, warm liquid flows through piping buried within the ramp, as seen in the figure on the screen. The heat is then transferred from the fluid through the concrete to warm the surface of the ramp. In this case, diluted glycol was chosen as the working fluid as it has both a low freezing point and a high heat capacity. Most standard hydronic heat systems reheat the fluid using a boiler after it has exited the heating zone. This, however, is an expensive and energy-intensive stage of the process. We as a group felt that it was important that the fluid be reheated using a renewable and/or wasted heat source found on campus, to be expanded on later. It was calculated that in order to remove winter precipitation at a rate of 4.2 millimeters per hour, a constant heat transfer rate of 71.9 kilowatts was required between the flowing glycol and the ramp surface. It was decided to divide the piping into 39 loops, each 3 ramp lengths long, parallel to the library wall, and can be seen in the figure on the left. Industry standards suggest that the piping within the ramp be spaced at 6 inches apart, center to center, and at a depth of 6 inches beneath the ramp surface. Using these values, a shape factor was calculated and was used in combination with the thermal resistance of the pipe and concrete material to determine the required temperature of the glycol. This value was determined to be slightly over 12 degrees Celsius and required a mass flow rate of 0.20 kilograms per second to constantly maintain the required temperature. Following the determination of the quantity of heat required, the next steps were to determine where the sources of waste heat on campus were located and which of them, if any, could successfully provide the required amount of heat to the ramp location.
The fluid selected for the project is a mixture of 40% propylene glycol and 60% water, which has a freezing point of negative 34 degrees Celsius. It was chosen due to its low freezing point, relatively high specific heating value, its non-toxic properties, and relatively low price when compared to mixtures with higher percentage of propylene glycol.
The University of Guelph campus has many pre-existing heat sources that can be used to provide the necessary heat energy for the proposed hydronic system. The University of Guelph campus has a large exhaust stack that outputs a large quantity of hot flue gas. This flue gas is a source of low-quality heat, which is capable of providing enough energy to effectively heat the glycol used in the hydronic system. To transfer this heat, a heat exchanger will be installed inside of the stack. The Guelph stack heat exchanger must be designed so that it is able to supply the required heat. As discussed earlier in this presentation, the heat exchanger must transfer 71.9 kilowatts of energy. In analyzing the heat exchanger, the main value that was to be calculated was the total surface area required of the heat exchanger. The area is dependent on the overall heat transfer coefficient, the total heat flow required, and the log mean temperature difference of the two working fluids. The log mean temperature approximates the average temperature difference across a heat exchanger. Temperature difference is the driving force behind heat transfer, so this value is key in understanding how the heat exchanger will behave. The log mean temperature is a function of both the inlet and outlet temperatures of the working fluids. The glycol entering the ramp must be 12.3 degrees Celsius at a flow rate of 8 kilograms a second to provide the ramp with enough energy to meet the snow melting requirements. These values were found in earlier calculations. Analysis of the heat exchanger used an outlet temperature of 15 degrees to add a factor of safety. While no data exists for the amount of flue gas exiting the university stack, a comparable stack found within the Guelph region was found to have an exhaust mass flow rate of 8 kilograms a second. This value was used as an accurate assumption of the Guelph stack mass flow rate. The temperature of the Guelph stack is known to be 40 degrees Celsius. Applying an energy balance formula allowed the inlet temperature of glycol and the outlet temperature of the flue gas to be calculated. With all inlet and outlet temperatures now known, the log mean temperature formula could then be applied. This yielded a log mean temperature difference of 21.7 degrees Celsius. Gas to liquid heat exchangers typically have a worse heat transfer coefficient when compared to liquid heat exchangers. Gas to liquid heat exchangers usually have heat transfer coefficients in the range of 250 watts per meter squared Kelvin. This will serve as a good estimate of the actual value of the heat transfer coefficient of the stack heat exchanger. For reference, a water-to-water heat exchanger typically has a heat transfer coefficient between 850 to 1,700 watts per meter squared Kelvin. Now, by knowing the heat transfer coefficient, heat flow, and the log mean temperature difference, the total required area of the heat exchanger surface can be found using Newton's law of cooling. This results in a final area of 13.3 meters squared. The last aspect of the heat exchanger design is the material choice. The design opts to use 1-inch diameter copper pipes that are 2 meters in length. This results in a total quantity of 84 sections of pipe. This choice of pipe is a good compromise between surface area to volume ratio and complexity of the heat exchanger. Copper is also an ideal material to use in a heat exchanger because of its high thermal conductivity of 385 watts per meter Kelvin, which is more than 7 times that of steel. Copper is also corrosion resistant to both water and glycol. The next step to discuss in the process of the hydronic system is the logistics of transporting the glycol between the central utilities heat stack and the library ramp.
Currently, the University of Guelph has an extensive underground tunnel system that runs all throughout the campus. These tunnels are kept at a consistent 40 degrees all year round. As you can see, the planned setup has the pipes from our system running through these tunnels to reduce heat loss and will surface only at the library where the heat transfer is needed. Following this, the cold water will be returned back to the heat exchanger where it will be heated again for reuse in the system. The system will have losses in 3 separate sections. First, the friction and head losses at the bends, point A to point C on the diagram. Second, friction and head losses through the ramp setup at the ramp. And third, the head losses from point A to point B. These values total to about 313 meters, which is accounted for with the purchase of the pump for the system. In conclusion, the current ramp setup for Winegard Walk has become a problem due to its difficult and inefficient winter maintenance, which involves a large amount of salt usage. The high usage of salt has led to negative impact on local wildlife and ecosystem and has led to structural repairs, with one such repair costing the university $100,000. In addition to this, the current ramp setup possesses a steep, outdated grade of 8.75%, which exceeds the provincial accessibility code standard of 6.7%. This has in turn led to significant accessibility issues during the winter months. Our proposed new ramp design will address and fix all of these issues. The implementation of a hydronic heating system will prevent the buildup of ice and snow, and the ramp will be rebuilt with a proper grade of 5%. The system will draw excess and unused low-grade heat from the central utilities heat stack to heat up the propylene glycol and water mixture. This mixture will be run through pipes underground in the pre-existing tunnels to the library ramp, where it will be used to eliminate the ice and snow buildup on the surface of the ramp.